Hello everyone and welcome back. My name is Mr. Koval, and in this video I'm going to be going over how to complete a Lewis dot structure by adding missing lone pairs and also how to identify bond angles and the hybridization at different atoms. So let's get started. Okay, so in this problem it asks us to complete the Lewis structure shown below by adding in any missing lone pairs, then identify the bond angles and hybridization of each atom indicated. So let's look at our molecule. So we got this long, big monster of a molecule here. And the first thing we're asked to do is put in any lone pairs that are missing. And so the way we're going to decide or figure out where the lone pairs go is that we want to give everything an octet. So remember, you want 8 electrons around the central atom, with the exception of hydrogen, right? So we'll look at each atom, determine if it's got 8 electrons. That's either going to be 4 bonds or it's going to be a number of bonds plus lone pairs. So that's why we need to put the lone pairs in first. So starting over here, this carbon has 1, 2, 3, 4 bonds. So each bond is 2 electrons. So that means that this carbon has 4 electrons, so it has an octet. This oxygen only has 2 bonds. There's nothing else. So that's 4 electrons total. But we want 8. That means it needs 4 more electrons. So we're going to have to add lone pairs to this oxygen. So we're going to add 2 lone pairs. And so now the oxygen has an octet. Same thing goes with this oxygen. So it's got 2 bonds. That's 4 electrons total. And we're going to add another 4 electrons, 2 lone pairs. So now the oxygens have their octet. Here we have a carbon. So when you're drawing organic molecules, the thing to remember is that where there's a corner and there's nothing written as far as an atom goes, the assumption is that there is a carbon there. That's the understanding. So here we have a carbon, here we have a carbon, here we have a carbon, 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 carbon. Okay, so when we look at this carbon here, we have 1, 2, and then a double bond. That's 4 bonds. So that's an octet because, again, 2 electrons per bond. So this one has an octet. This one also, same situation, 1, 2, 3, 4. So that has an octet. This carbon has 1, 2, 3, 4. Again, 1, 2, 3, 4 for this carbon. 1, 2, 3, 4 for this carbon. 1, 2, 3, 4 for that carbon. So all of these carbons have 4 bonds and therefore an octet. Okay, so what about this carbon here? The thing to keep in mind is that when you have this more condensed version of your formula, this hydrogen is actually bonded to the carbon like this, right? So you could see that these 2 hydrogens are bonded to the carbon. You could have written it as CH2 with a bond after that. But either way is fine. So this hydrogen is bonded like this to the carbon. And so that's going to be 1 bond plus this bond here, that's 2, plus the double bond that's to the carbon. So this has 4 bonds. So this carbon has an octet. The same thing for this carbon here. So this hydrogen is bonded to that carbon. And again, for organic molecules, the kind of the rule of thumb is if you have an atom that follows a carbon, it is bonded to the previous carbon that it's following right after. Okay, so this hydrogen is bonded to the carbon. This carbon is bonded to that carbon. And then this carbon is bonded to that carbon by 2 bonds. So we got 1, 2, 3, 4. So that carbon is bonded 4 times, so it has an octet. And same thing for this one. So this hydrogen is bonded to the carbon, so that's 1 bond, plus the single bond here, that's going to be 1 bond, and the double bond. So this carbon has 4 bonds. And same thing here. So this hydrogen is bonded to the carbon. This carbon is bonded to the carbon, so that's 2 bonds, plus these 2 bonds, that's 4 bonds. So each of these 4 carbons has an octet. Finally, we're getting to the end. So this carbon here has 1, 2, 3, 4. So that has an octet. This oxygen has 1, 2 bonds, nothing else. So that's 4 electrons. It needs 4 more. So we're going to put 2 lone pairs. So 1, 2. So now the oxygen has a full octet. This carbon has 1, 2, 3, 4 bonds. That's an octet. And then this nitrogen has 1, 2, 3 bonds. That's 6 electrons. It needs 2 more. So I'm going to put 1 electron or one lone pair on the nitrogen. So now that we've filled everything in with the lone pairs, now we need to figure out the bond angles and the hybridization. Okay, let's get started on that. So with regard to bond angles and hybridization, it's all going to come down to the number of bonding and non-bonding pairs around your central atom, and which is going to determine by VSEPR theory what the shape around that central atom is going to be. You can't look at the molecule and say, oh, look, this is going to be linear, or this is going to be triangular, or anything like that, because this Lewis dot structure does not give you an accurate picture of what the angles are. So you have to use your VSEPR theory chart if you've got it handy, or if you've got to memorize it, then you should have it memorized. If you don't have it memorized, then go ahead and use your VSEPR chart. But that's going to be the key to understanding the bond angles and the hybridization. So let's get started. So bond angles for A, where's A? A is here. So the bond angle, we're going to determine that by VSEPR, right? So remember, for VSEPR, to get the shape of your molecule or the electron group geometry, you have to look at how many total electron groups there are around the central atom, and then determine what the electron group geometry is going to be. So here for the oxygen, or I'm sorry, for this carbon here, which is this, we want to know this angle here. Well, this is the carbon, the central atom. And remember, double and triple bonds are considered one group, one electron group, not 2, right? Triple bonds are 1 electron group, not 3. So single, double, and triple bonds are all treated equally as far as the number of groups go. They're all considered one group. So I have one group here. This double bond is a second group, and I have this single bond a third group. So I have 1, 2, 3 groups around the central atom, the carbon. And so since I have 3 total groups, 0 lone pairs, so when I look on my VSEPR chart, the electron group geometry is going to be trigonal planar. And when you have a trigonal planar molecule, that's going to be a 120-degree angle. So that's going to be 120 degrees. Next, for B, we have this angle here. Now, don't let the picture fool you in thinking that this is a linear and it's 180 degrees. That's not the way it works. So again, we have to pay attention to how many groups, electron groups, do we have around our central atom. So this carbon is my central atom. This hydrogen is bonded to the carbon, right? So again, I could redraw this like this. So then this hydrogen is bonded to the carbon. This carbon is bonded to this carbon by a double bond, and this carbon is these carbons are bonded by a single bond. So I have 1, 2, 3 electron groups around my carbon here. So again, if you have 3 electron groups, no lone pairs, then the electron group geometry is going to be trigonal planar. And again, the bond angle is going to be 120 degrees. Now, because of this double bond will take up more space. And so technically, it's probably going to be less than 120 degrees. But the ideal angle would be 120 degrees. So you might put less than 120 degrees, or if your professor or teacher isn't want to be that picky about it, then 120 degrees is the ideal angle there. C, we have this angle here that we want. Again, our central atom is carbon. We're going to count the total number of electron groups. So the double bond here is 1 electron group. This single bond is a second one, and this single bond is a third one. So we have 3 total electron groups around that carbon. So once again, if you look on your chart, your VSEPR chart, any molecule that has, or central atom that has a total of 3 electron groups, the electron group geometry is going to be trigonal. Is going to be trigonal planar. So here, this is going to be trigonal planar, and again, the bond angle here is going to be 120 degrees, or technically probably less than 120 degrees, a little bit less than. But again, 120 degrees is fine if you're not being picky. So this is going to be 120, 120, 120 so far. And then D, this angle here. And again, it looks like it's a right angle of 90 degrees. That would be false because, again, this is a 2-dimensional picture of a 3-dimensional object. And so again, we're going to count the number of electron groups. So we have 1, 2, 3, 4 total electron groups that are all bonding, no lone pairs. So the electron group geometry and the molecular geometry will be identical, and that is tetrahedral. So because this is tetrahedral around the central atom there, the angle there is going to be 109.5 degrees. Okay. And then finally, E, this angle here. Once again, you want to count the total number of electron groups. We got 1, 2, 3 bonds plus the lone pair. That makes 4 electron groups. So once again, the electron group geometry here is going to be tetrahedral, but the molecular geometry is going to be trigonal pyramidal. But here we're interested in the electron group geometry because we want to know the angle here. So the ideal angle here for tetrahedral is 109.5. Now the lone pair there, just like the double bonds, are going to take up more space. They're going to push the others away. So these are going to be closer together. So technically it's going to be less than 109.5, maybe 107. But again, probably not a big deal for this problem here. Okay, hybridization. Well, how do you determine hybridization? Let's remind ourselves that when you're hybridizing, what you're doing is you are basically taking a certain number of atomic orbitals, you're hybridizing them together to get some hybrid orbitals. And so the orbitals are going to be s and 3p's and then you have 5 Ds. And what you do is, the idea is that for every electron group around your central atom, you need that many molecular hybridized orbitals. Well, the way you get those orbitals is by taking the atomic orbitals, and you always go from the lowest energy moving to the higher energies. So S orbitals are lower in energy than the P's, which are lower than in energy than the D's. So we're going to take the number of atomic orbitals that we want and then hybridize them, and we'll get the same number of hybrid molecular orbitals out. So whatever you put in, you get that same number out. So if you put in 3 atomic orbitals, then you're going to get out 3 equal energy molecular orbitals. So let's go ahead and do F. So F, we have F here. Now, how many electron groups do we have? We have 2 bonds, 2 lone pairs. So we need a hybrid orbital for each of those electron groups. So since we have 4 total electron groups, we're going to need 4 atomic orbitals to hybridize. So that means we're going to need an S. And notice I'm working my way from the lowest energy to the highest. So we're going to need an S, a P, a P, a P for my 4. So then when I hybridize those, I'm going to get 4 equal energy sp3 hybridized orbitals. So then for F, that atom is going to be sp3 hybridized. Okay, what about G? Here, G, we have this carbon here. And again, just to make it clear, this hydrogen that they have is actually bonded to the carbon, like that. So now I can count the number of electron groups. So I have 1, 2, 3 electron groups. So that means I need 3 atomic orbitals to hybridize together to get my 3 hybrid molecular orbitals. So in this case, I'm only going to mix together the S, the P, and the P. So then these are going to be hybridized, and I'm going to get 3 equal energy. Notice I have 1, 2, 3 atomic orbitals, so I'm going to get 3 equal energy sp2 hybridized orbitals. Okay, so then this carbon here is sp2 hybridized. And now I want to point out something with regard to the double bonds and triple bonds. For double and triple bonds, one of the bonds is always going to be a sigma bond. What does a sigma bond mean? That means just that you're going to have an overlap along the axis directly between the atoms that are bonded together. So that's why we call it a sigma bond. So the sigma bond overlaps, those are going to be due to orbitals overlapping along the axis between the 2 atoms. And you can only have one of those. You can't have more than one sigma bond because you can only have you can only have an overlap of orbitals one time between those atoms. Anything else is going to be pi bonds. What is a pi bond? Pi bonds are going to be due to the overlapping of unhybridized p orbitals. So what I want to point out here is, notice that I took the S, the P, and I made 3 equal energy sp2 hybridized orbitals. But notice that I have 1 unhybridized orbital left over. That unhybridized orbital can be used to form pi bonds, and that's what you see here in the double bond. So the double bond here is going to have 1 sigma, and that other bond in the double bond is a pi bond that's created by the overlap of unhybridized p orbitals on this carbon and that carbon. Okay, so I just wanted to point that out here, that we have that unhybridized p orbital left over, and so we have a pi bond there. Okay, so then now for H, where's H? H is the nitrogen here. And so again, we're going to count the number of electron groups. 1, 2, 3 bonds plus the lone pair. That's 4. So again, we're going to need 4 atomic orbitals. So we need 1, 2, 3, and 4. So again, we get 4 equal energy sp3 hybridized. And so we're going to put sp3 hybridization. Okay, so now for the last question. How many pi bonds are in this molecule? Well, I kind of gave it away. The pi bonds are going to be in the double and triple bonds. Because remember, for single bonds, you just have a sigma bond. So all bonds are going to have a sigma bond. Single bonds are sigma bonds. But then if you have a double bond, you're going to have one sigma bond, and then the rest are going to be pi bonds. You can't have more than one sigma bond. So if you have a double bond, then you got a sigma and you got a pi. If you have a triple bond, then you've got one sigma and 2 pi. Okay, so all you have to do is count up all the extra bonds that you have in your double and triple bonds. So here I have 1 here, 1, 2, and 3. That's 4, 5, and 6. So I have 6 pi bonds in this molecule. Now, if they asked for the number of sigma bonds, you basically are going to count all the bonds, because all bonds between atoms is going to have one sigma bond and only one sigma bond. So here, this would be 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, right? 16 for that hydrogen, 17, 18. I already think I counted that one. 17, 18, 19, 20, 21, 22. Oh, yeah, 21, right? I don't want to count the pi bond. 21, 22 for that one, 23, 24, 25, 26, 27, 28, 29, 30. So it looks like we have 30, unless I miscounted, which may be the case, but it looks like we have 30. But we definitely have 6 pi bonds. And so that's it for this video. That's it for this problem. I hope this was helpful. If you enjoyed this video, if this helped you in any way, then please, by all means, like the video, share the video, hit that like button over here somewhere. Also, do me a favor, subscribe to my channel if you haven't done so already. And also, hit that notification bell. When you do, click all so you can be notified by all the videos I put out. Finally, put a comment down below in the comment section. Let me know what you think. Ask me questions. I would love to hear from you. If you have a question or a problem you need help with, or if you have a topic you need me to cover, then put that down below. I would love to do that for you. Thanks for joining me, and have a great day.